Welcome to Southeast Queensland Skies. Today I'm going to be going through the following. Why is an alt-as mount not so good for astrophotography or electronic assisted astronomy? Another way to put that would be, what is field rotation? So in order to explain this, I created myself a PDF file a long time ago when I was a kid learning how to do astronomy. And here's the drum. I think we've all probably seen these sorts of photographs, star trails, where the person points the camera towards a celestial pole, either north or south, and takes a 1 hour or an hour and a half exposure. And you see all these beautiful circular star trails up in the sky from the exposure. Now that's not due to the heavens moving, it's due to the Earth rotating while the heavens are fixed. And the fact that we're rotating about our axis, on the Earth's axis, we get to see these star trails, and they're circular in the sky. Alright, so what does that have to do with it all? Well, if you imagine an object, this is the Orion Nebula. Early in the evening it might be over at this part of the sky, later in the evening it's up there, and even later in the evening it's over there. Now in actual fact what's going on there is it's actually still taking one of those circular orbits in the sky. Here we go. See that? It's still a circular path. I shouldn't have said orbit, a circular path through the sky. And you can actually see that the little red part of the nebula, just above my mouse there, a little tiny section, or indeed the fan is almost perpendicular to the path of the sky, is the same in every shot. See? The path, that curvy part of the nebula, is perpendicular still to the path. That perpendicular section is still perpendicular to the path, and that is because, as I said before, the object is fixed in space. But because we're rotating under it, it appears not only to take this circular path, but also to change its orientation. It's that way over in the east, and that way kind of overhead, and that way over in the west. And what does that again got to do with it all? Okay, an equatorial mount follows those circular paths because it has an axle called the RA axis, right ascension axis, and you can see in different parts of the sky this little equatorial mount that I use to demonstrate this just simply follows a circular path. And what that does is, if we have a look at this, okay, it keeps the scope and camera in the same axis as that counterweight. Never changes, but the counterweight and everything is rotating in a clockwise, in this case, circle. So if we have a look at this image right here, you can hold your head vertical, right? Your neck, your head are all vertical, and you can align yourself with that, with the cord of the camera coming out of the top. So if you imagine that cord coming out of the top of your head. In this photograph, it's like you've pivoted right at the base of your neck, not turning left or right, but pivoting, tilting your whole head over to the left, so that your head's now held in that kind of orientation, aligned with that counterweight axle. And if you glance down here while holding that position, you'll see that's the sort of frame it would take, the image it would take at that orientation. Indeed, the cord for the camera, the power cord, would be coming out of the top of your head or out of the top there, just like it is there. Now, a few hours later, you can hold your head normal, vertical, upright again, and that's the kind of image you'd be taking. Cord coming out of the top of your head, like coming out of the top of the frame, just like it is. Hours later, you pivot again at the base of the neck, but this time tilt your head well over to the right, till it's aligned with that axle or that counterweight, and sure enough, that's the frame you'd take. Okay, now the thing is, if you look at those three photographs taken at vastly different times of night, you find that they actually are exactly the same image. Relative in every frame, this little tiny red nebulosity down at the base is always in the same position. The fan sort of thing is always in the same orientation. And there we go, just to glance between both of them to prove it to yourself. Keep tilting your head and you'll see what I mean. So what that means is an equatorial mount can take very, very long exposures. It will track that object through the sky, and every exposure is pretty well lined up with each other exposure. Of course, one mount might have far better gears, far more precisely machined gears, far better motors, far better motor pulses, and track a lot better than others. Okay. However, while it can do these long exposures, the aberrations in the quality of those gears and those motors means that, generally speaking, an average general rule of thumb is that anything past 90 to tops 120 seconds, anything above that, you will need to auto guide. And that's where you get another camera, another telescope mounted on top of your normal camera, and it picks a star and looks at the brightness of that star in individual pixels in that auto-guiding camera, so it can send unique, special, highly adjusted pulses to the motor to compensate A, for the bad motor pulses or the inaccurate motor pulses in the original mount, but also to cater for the fact that the gears might not quite be turning at the appropriate speed. So it kind of takes over from your mount's inherent motor and gear set and guides it much more accurately. And you need that, as I said before, if you go generally above 90 to around 120 seconds. Less than that, many mounts, most equatorial mounts, you can get away unguided. Okay, right, but what about Alt-Az? Here we go, here's my little Alt-Az Celestron unit, and this time it doesn't track through the sky in a circular arc, it simply looks left, so that's like holding your head vertical. This time, instead of pivoting at the neck and tilting your whole head, your head is still vertical, held upright, and like looking left at traffic lights, you're just looking to the left. And over in this shot, you're just looking to the right. And in the middle, you're kind of looking up. But your head is vertical all the time, and that leads to these sorts of images. Right? 3 images taken on an alt-azimuth mount. And you can very quickly see what's going to happen. The image in each frame, as you can see by me pointing them out, is now totally different. Think of this fan. Here it's pointing in this direction of my mouse. Here it's pointing in this direction of the mouse. And over here that fan's in that direction. Okay, but with an Alt-Az mount you're still tracking. It's still got motors to track. The thing is, it's tracking to the best of its gear set and motor pulsability. It's tracking kind of like the middle of the nebula. It's in the same spot in every photograph. It's the edges that are actually rotating. Between that photo, that little red bit has travelled up around here until it's in that position, and then between then and the next photograph it's kind of travelled around until it's in that position. So all of the parts of this nebula are rotating about a central part of the nebula. The Alt-Az mount is still tracking that middle, but it's unable to actually do that rotation, get rid of the rotation. Consequently, much tougher to do astrophotography and EAA with an Alt-Az mount. The mount might follow and track the object, but it cannot account for this field rotation which is occurring because the mount itself can only go left and right and up and down. Okay, so this leads to a generic thing you read on the forums. You can only take astrophotographs to a maximum of 20 seconds with an Alt-Az mount. Now I'm telling you that's not true. I will post up a link to my Flickr account. I have a publicly available album called Alt-Az Maximum Exposure Timetables, and it says these are the maximum times for various latitudes, either north or south of the equator, but may vary with your mount's gear precision, drive motor precision, and camera pixel size versus the optical tube assembly's focal length or magnification. And it says start with the times as per the table for a particular altitude and azimuth of an object and take test shots to determine for your mount. So what have we got here? Let's have a look. Starting on the left, this right to the left there, it tells you the name. That is the alt-azimuth times for latitude 10 degrees north or south of the equator. Next one is latitude 20 north or south, and so on, latitude 30, 40, 50, etc. I'll tell you about this coloured one later. So let's pick latitude 30. First up, these are all calculated, these maximum times are calculated for different objects at different part of the sky. Remember I said you're not just limited to 22nd. So if I go back to my PDF, I'll show you what I mean. Let's go back to that first image. Take an object, a star in this case, down here. See how the star trail is very tiny? Okay, so for an hour it's only moved a relatively small amount, as does any field rotation. If you were tracking that in alt-azimuth, the field rotation, the rotation about the centre of the picture, only rotates little amounts. Compare that to this big star trail out here, or even out here. It's the same 1 hour later, but because it's way out in this part of the sky, the movement is huge. So is, still in the same time, 1 hour exposure, but you imagine the rotation effect is likewise much larger in this part of the sky than it is down here. Okay? Right, so let's have a look at latitude 30. Now, these are calculated from a formula for a particular pixel size in a camera and for a particular magnification. So these are approximate but a great starting point. So what do you do? Well, you can look at a target at a particular bearing or azimuth anywhere from 0, true north, through 10 degree increments right up to 90, and you cut across this way, up again to 100, up to 180, cut across this way, 190 all the way to 270, and then back again 280 all the way to 360. So objects that are, let's have a look at this, somewhere between 0 and 10 or 5 to 15 are in that row, as are 165 to 175, as are 185 to 190, as are 345 to 355. Likewise, the altitude, anything up to 10 degrees is in that column, anything 10 to 20 altitude above the horizon, that column, and so on and so forth. And you can therefore see that if you were pointing absolutely north or directly south, remember 360 is like north, that directly overhead at the zenith, 90 degrees altitude, you really can't get a shot. It's got huge rotational star trails around the edges of the frame. Whereas pointing right down just 10 degrees above the horizon, you can go 34 seconds maximum as per the formula. Okay, get the gist? So this means that through the night, if you jump there and you decide at your site, you hop over and you jump to a target that's down in this area of the chart, these sorts of bearings, this sort of degrees, generally you're very limited in the exposure time. And down there at those exposure times, you're highly unlikely to get enough photons of light to enable you to take a decent enough image, even at very high gain on the camera. Whereas in the other parts of the sky, down in these sorts of bearings or azimuth and these sorts of altitudes, you can get very long, as per the formula, long exposures like 391 seconds. Now, before you get all excited on that, that is not possible with alt-az mounts. Again, because of the limitations, they're usually the cheaper style of mount built mainly for visual observing, and as a consequence, the gear teeth, the motors, the motor pulses are built with less precision. And I've yet to see anyone go past a 60-second or 65-second shot in alt-azimuth for an open single exposure without getting significant star trails. Depends on the camera, depends on the scope. And that's why I say this is a starting point for a table. So what I would suggest to you to do is the following. First up, okay, pick a table that suits your latitude, and like those degrees of bearing and altitude, this 10 degrees would work for anyone from 5 through to 15, north or south of the equator. This 20 would work from 15 to 25, 30 from 25 to 35, and so on. So in my particular case, I'm at 27.5 south. I chose the latitude 30 table. See what it looks like? Except I did the following to it. Same table. Okay, I coloured it. I completely blacked out the column that said I couldn't get a shot. And because I have a very sensitive ASI 224 camera, which can take 5-second shots, I kept the sort of 0 or 1 through to 10 range, but I put it as red to highlight very short exposure, not a lot of photons in the shots. Very high gain needs to be taken with those areas of the sky. Then I chose 10 to 20 and put it as orange, and so on and so on. So if you've got a DSLR camera that cannot get down and get any decent imaging at 5 seconds, you would black this area out and maybe take 10 seconds and above, or even 20 seconds and above. So you're going to end up with a table that starts at some point for you. If I say a very low sensitivity DSLR, it might be the 20 to 30 range, and everything under that is blacked out. On the high side here, at one point I did actually make every one of these big numbers 60 seconds. Every one. I've left it in this particular example, but I made it 60 seconds because, as I said, for my particular scope and camera combination and others I've seen where people have been broadcasting or putting images on the web, likewise, I've never seen people go really successfully past 60-65 seconds. There'll no doubt be some gurus who post up, "That's stupid, Mr. Smith. I've gone, and post up that they've done so." That's true. Remember, I'm talking in the main, in general. As a starting guide, these are fantastic. And that leads on to how do you use this in the field? Well, what I do is I go out with a laminated copy of this. And let's say it's 10 o'clock at night when I set up my little Altaz rig. And I look up my list of targets that I'd like to go and have a look at, because I do EAA rather than astrophotography, and I find that the target's down in this area where it's pretty slow. So what I do then is I have a look at my stellarium and see if that object goes lower in altitude or different part of the sky where it's going to get more exposure times. So I decide I'll leave that to later when I can get a longer exposure. Now, whether you agree or disagree with all of these numbers, that holds true. Okay, so let's suppose later in the evening it's at 30 degrees and I look and I go, 32-second shot. I know I cannot get that, but it's a guide. I'll click off a 30-second shot and have a look at what I get. If I get bad star rotation or field rotation, I'll choose 25 seconds. And if it's still apparent and bothers me, I'll go down to 20 seconds and so on. Just a couple of shots and I'll be there. But that's a great starting point, and it's not 20 seconds necessarily, okay? Or maybe I start and I look and I go, gee, it's there, and I find out that it's setting and I really should have come out earlier in the evening. So I might say, right, later in the evening it's just getting higher and higher, and I'm going to go to bed at midnight, so sorry, I'm not going to hang around for that. So you decide, well, gee, I should have come earlier in the evening when it was down lower, and I could have got a longer exposure. And indeed, due to different seasonal variances, the way the axis tilts, there might be an object which I really struggle, like a galaxy, to get with multiple, let's say where it says 35 seconds here. Let's suppose I had to take a 30-second shot before I got something decent. No star rotation, no field rotation. So I might say, well, it's so faint I didn't get a decent shot. But later in the year, because of the tilt of the Earth, it might slightly change the azimuth, the bearing, the arc of the circle that it goes through the sky, and I might find it up in this area at 47. So I decide, great, I'll put a little note in my diary to shoot that galaxy, the faint galaxy, later in the year when I can see it's up around that degree up around that time there, because the whole azimuth has changed a bit because it's gradually, because of let's see, that would be summer, I think. Anyway, different season when it's up in that area of the sky, and it might not be 47 seconds, it might only be 40 seconds that I can take before I get field rotation. But it's a very handy table to use, and I would be shooting at 40 seconds as against just accepting the verbatim 20 seconds is the rule. It's not. There are different parts of the sky where you can shoot longer, and this is a guide. And remember, these big numbers, you cannot get them. You should start assuming they're all 60 and just try a 55-second shot, see what you get. And I'm sure even up in this area that says you can go 391 seconds, I'm sure that around about that 65, due to those aberrations in the gear teeth and the motors and the motor pulses, that you won't be able to get that even on a very high quality mount, alt-az mount. But that's the reason why you are limited. It's not impossible, but you are limited to the exposure times in different parts of the sky due to field rotation with an alt-azimuth GoTo mount. I hope you guys have found this interesting. Thank you very much for watching.